Hello, everybody. So Professor Guruprasad will give his third lecture now.
So good morning to everyone. So you can see the title. This is Bell-Kochen-Specker theorem, and as I told you earlier that Bell discovered his theorem in 1964, and maybe Kochen-Specker discovered maybe in 1967. But Kochen-Specker theorem, I will try to tell in which way it is different from what Bell discovered, even for contextuality. So these people performed experiments on testing Bell violation of Bell's inequality. Actually, Clauser started this thing. Then Aspects in 1980s performed some good experiments, and finally Anthony Zeilinger performed maybe one of the most beautiful experiments. And all these results shows that there is contradiction between quantum mechanics and Einstein's conception about nature. So let us start with these quantum rules. So some of the features of quantum mechanics. So nature does not allow joint perfect spin measurement along different directions. We know already that earlier it was discovered that at least Heisenberg tried to tell that perfect joint measurement of position and momentum is not possible. And for some time, Einstein was fighting that no, joint measurement of position and momentum can be performed. And there had been big debate, but finally Einstein accepted that maybe nature does not allow joint measurement of some, perfect joint measurement of some observables. But we will confine ourselves within this spin-up particle. And measurement result already, you know, that is one of the eigenvalue of the corresponding self-adjoint operator associated with the observable. And it happens with a probability given by Born rule. And measurement in general disturb the quantum state. Now consider this symbol you don't consider to be a vector along z direction. This is just a symbol. It is the quantum state, which is a up eigenstate of sigma z. So denoted by z0. Now, if you perform spin measurement on this particle, then of course, with 100% probability you get up. So you can tell that 100% probability, that means sigma z is the property of the system, because if this is the state, whenever you measure spin along z, you get up. But what the problem is, if you perform spin measurement along x, then some of the time you get up, some of the time you get down, and with equal probability. And in general, if you perform some general direction, denoted by theta phi, then with cos square theta by 2 probability you get up, and sin square theta by 2 you get down. Now, interpretation of quantum mechanics, at least Copenhagen interpretation to consider, then if you prepare particle in K0 state, then each individual particle does not have definite spin along x. Measurement only creates the result. So if 0 is my state, and if you perform sigma x measurement, you get up or down. And quantum mechanics tells that before the measurement, particle did not have any property for sigma x. Only measurement only creates the result. It may create up or it may create down. But before the measurement, sigma x has no reality. But Einstein was always thinking, maybe till his death, that particle finally have properties. individual particle have properties. Quantum mechanics may be consistent, but it is incomplete. That I will discuss. But for the time being, you see that if I picture this thing in this way, that I tell that individual particle have pre-existing properties for both sigma x and sigma. But nature is such that if you prepare many particles in get zero state, then this individual particle, or for all the particles, sigma z has definite value, but sigma x will be distributed with 50% probability for up and 50% probability of down. So sigma x has also definite value, but nature is such that if you prepare an ensemble, then half of them will have sigma x is equal to +1 and half of them will have sigma x is equal to -1. If this is the picture, then can you disprove it if someone claims that sigma x has also reality for individual particle? How quantum mechanics can contradict this picture? And that property will be revealed in the experiment measurement. So again, you will get a sigma x up with 50% probability and sigma x down with 50% probability. So this picture cannot be discarded immediately by quantum mechanics. Even if I consider another sigma, and if its probability is 30% for up and 70% for down, I will again assign those sigmas +1 with 30% of the particle have sigma, that sigma equal to +1 and 70% is -1. Like that I can do. How quantum mechanics can contradict that? Individual particle, of course, quantum mechanics is successful. It is consistent with all the experiments that have been performed. But this kind of picture cannot be discarded immediately, at least by performing measure. Bohr and Heisenberg and their co-worker used to believe that such picture cannot exist. That picture, they told that no, that kind of picture cannot exist. And von Neumann, in 1932, in his very famous book, Mathematical Foundation of Quantum Mechanics, he claimed to have proved that dispersion-free state is not possible. That means a state for which every observable will have definite value is not possible. And for that, actually, he took three assumptions, right? He defined an expectational functional, which if you consider self-adjoint operator, it is real. If you consider where alpha, beta real and AB are self-adjoint, but they may not commute, then it has to satisfy and so E is some expectational functional, identity is equal to 1. With this thing, he showed that this expectational functional has to take this form. So finally, quantum state is the only solution. So, and quantum state, if quantum state is the only solution, you know, quantum state is not dispersion-free. For some of the state, if it is the eigenstate of some observable, you can assign reality, but for other observable, we don't commute with this observable, you cannot. Now, Einstein for some time challenged, as I was telling you, the impossibility of joint measurements of some observable like position and momentum. But at one point of time, he accepted this impossibility imposed by nature, but never, this is very important, but never accepted the impossibility of quantum system having definite values for observable to be revealed in measure. Einstein is telling, okay, nature may not allow some observable to be jointly measured, but that does not tell that particle cannot have definite values for those observable. It does not logically follow, at least. That you cannot measure, that's why particle cannot have that. And there are very extreme kind of experiment statement. So observation, as Pascal Jordan, observation not only disturb what has to be measured, they produce it. we compel the electron to take a definite position. Like before my measurement, electron does not have any position. And when we perform the measurement, we actually compel the electron to take a definite position. And we ourselves produce the result of it. It's bore. It is wrong to think that the task of physics is to find out how nature is. Physics concerns what you say about nature. And Einstein used to tell that God does not play dice with the universe. And some people tell that Bohr possibly told that Einstein should not advise God what to play. Like that, there had been many interesting statements. Now, quantum mechanics, as we know, this is a probabilistic theory, but Einstein used to believe that any fundamental theory will, if it is fundamental theory, then it has to be realistic. That means observable should have definite values for individual system. And also we should respect this locality. That means some disturbance on this particle cannot change the result of some measurement on the other particle. And measurement finally does not create but reveals predetermined values for observable. And in 1935, Einstein, Podolsky, and Rosen, using the idea of reality and locality, tried to show that quantum mechanics is incomplete. Einstein, maybe for some time, Einstein was thinking that there will be some feature of non-locality in quantum mechanics. Maybe he was thinking for some time. But finally, they came to the conclusion that quantum mechanics is a consistent, but it does not capture the whole reality. And reality, Einstein actually defined in their paper. So if without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of reality corresponding to that quantity. So reality, for some purpose, he is defining. Reality means, according to his belief, particle observable has a definite value for an individual system, but he is very careful when, because he is trying to prove that quantum mechanics is incomplete, he is very careful and giving this definition. And locality, if systems are especially separate, the disturbance on one system does not instantaneously affect the reality. That pertains to the other system. And criterion of completeness, every element of physical reality must have a counterpart in the physical theory. Then how they proceed? They took an example from quantum mechanics. And by using criterion of reality and locality, they claim to have proved that some kind of reality is there, but quantum mechanics cannot capture that reality. That's why quantum mechanics is incomplete. It is their argument. So it is something like this, but it is argument. It is not something that you should test in the lab. So you consider, actually I could have written the state that 5+, you can take 5+. So results are completely correlated if both measure spin along same direction. If both measure sigma z, either they both get up or both get down. And similarly, if both perform sigma x, or either both get up or both get down. Due to correlation, by measuring sigma z on particle 1, one can predict the result of sigma z measurement on particle 2. But late, so a state is 0, 0 plus 1, 1 that we are discussing. So late, Alice, who is far away, she measures sigma z and got +1. Then immediately she can infer that if you measure sigma z on the other particle without touching, because see the definition. If without any way disturbing a system, we can predict with certainty. So I am measuring sigma z here, but I can predict result of sigma z measurement of the other particle, even if it is light years. But it is argument that because I am not disturbing that particle. I can tell what is the sigma z value by performing measurement. I could have done similarly for sigma x also. But actually, I don't need perform any measurement because my argument is telling that already the value is there. I cannot, because I am doing this measurement from far away, and according to locality, I should not disturb. I cannot disturb the reality that pertains to the other system. So already, independent of measurement, the other particle has definite value for both sigma x and sigma z.
I apologize. This presents Einstein as an idiot, and I don't think that Einstein was an idiot. So as early as much before the EPR, in the Solvay conference of 1926, where he had the single particle box paradox, he already concluded that either quantum mechanics is incomplete, as it's written here in the box, or quantum mechanics is non-local. Yeah. So he admitted that there are the two possibilities are there.
But there he uses just a single particle. Single particle.
But still, I mean, if it calls for single particle, for sure, calls for two particles. Possibility. But like he admitted, either that or the other.
Yeah, there may be this non-locality argument may be idiotic, but here he is using two particles, so argument is more powerful. So conclusion is the reality for sigma z for particle 2 was already there. The same argument can be made for sigma x measurement also. Then for a single particle, both sigma z and sigma z will be real, but quantum mechanics cannot accept this. Because quantum mechanics are, no, they are non-commutating observables. So there is no common eigenstate. So both reality cannot be assigned for a single particle. So now their conclusion is okay. So maybe quantum mechanics is a very good theory, but maybe it cannot capture all the reality that are there. So it is incomplete. Now let us see what is the program of this hidden variable theory. Program of hidden variable theory is a mathematical construction. Question is quantum mechanics is working well. Question is whether more fundamental theory can be constructed, at least in even mathematics. And von Neumann told that. Von Neumann claimed to have proved mathematically that you cannot do. Quantum state is the final description of physical system. So what is the program? Program is something like that, program of hidden variable theory. So you have to create dispersion-free state, but finally you have to reproduce quantum mechanics, because quantum mechanics is consistent with all possible experimental results. So finally you have to reproduce quantum mechanics, otherwise it will be a useless exercise. So according to hidden variable theory, say you have prepared an ensemble of psi, but actually in the fundamental level, there is another parameter which maybe you don't know. And if you know both the parameters, psi along with that unknown parameter, then you can exactly tell what is the value of sigma z, what is the value of sigma x, or what is the value of some other sigma. Because we don't know those lambdas, that's why we don't know what is the value. So knowledge of psi and lambda provide definite value for all possible observations. So for any self-adjoint operator, you take A. If you know psi and lambda, then you can assign a value. But value cannot be arbitrary because measurement results only one of the eigenvalues. So there is a restriction that this value has to be one of the eigenvalues of A. Because when you are assigning value, that has to be revealed in measurement. So, and we already see that measurement are one of the eigenvalues. So there is a restriction that value assigned by this hidden variable theory has to be one of the eigenvalue of A. But finally, as I told you, we have to reproduce quantum mechanics. So there will be some distribution of lambda. And so finally, you have to reproduce this result that it corresponds to Born rule with some probability distribution of lambda. Probability distribution lambda. rho lambda. So this is the program of the hidden variable theory. But see, von Neumann told that, no, this kind of theory cannot be possible. Psi is the final description. And most of the physicists accepted von Neumann's argument. And there is a quote from John S. Bell published in Review of Modern Physics. Now you see the other way around. John S. Bell is telling maybe von Neumann's proof is idiotic. Yet the von Neumann proof, if you actually come to grips with it, falls apart in your hands. There is nothing to it. It's not just wrong, it is silly. When you translate this into terms of physical disposition, they are nonsense. See that words he has used. You may quote me on that. The proof of von Neumann is not merely false but foolish. No, this is not in the paper. This paper is this thing. This quote is from some interview. They'll possibly died in 1990 or 90. And actually, I'm not showing it. Actually, von Neumann told that this assumption is silly. This is true, this expectation is true at the quantum level, but at the more fundamental level, hidden variable level, it need not hold. And he actually explicitly showed that this is a silly assumption. Middle assumption is a silly assumption. It has to be true for quantum mechanics. So every hidden variable theory has to reproduce this relation on the average level, but not at the fundamental level. And Bell gave a nice proof. But this is nothing but another sigma, which makes 45-degree angle with x-axis. Now, von Neumann is telling that, but it is true that in quantum mechanics, this is true. But it has to be true in the fundamental level. Fundamental level, that means psi lambda, it assigns values, not average. So if you go to psi lambda level, then it will mean, and values has to be one of the eigenvalue. So in the fundamental level, it has to be like this. And they can never be equal. Question is, hidden variable theory will give definite value, and then I will integrate rho lambda, d lambda. Then I have to reproduce quantum mechanics. But not only that, Bell constructed a model where he considers spin observable, and he shows that you can construct a theory where every observable will have definite value and indeed reproduce quantum mechanics. So let psi is the eigen. So psi you can associate every pure state with a vector 8 in the block sphere. So you can denote the state by n. And if you perform, so if n is your state, say n is your state, and you are performing measurement along some direction n, then what is the probability of the up result? It is half 1 plus n dot m. And what is the probability of down result? It is half 1 minus n dot m. This is Bond rule, and you can calculate the average. Average will be very nice, n dot m. So this is very nice that finally your expectation value or probability is a function of just a scalar product in R3. And Bell constructed a model. This is not exactly what Bell constructed. This is a little bit complicated. I have taken this proof. I have taken this model from a book by Beltramithi and Casileni, The Logic of Quantum Mechanics. So here, this is very simple. So this lambda here, it is a scalar, but originally what Bell considered lambda is again another unit vector. That's why that model is a little bit complicated, but here it is very simple. So your state is n, which corresponds to quantum state, and some lambda, which is a scalar taking value from -half to +half. And the distribution is uniform. So lambda can take value from -half to +half. And the value, so you are giving a value assignment. Value assignment rule is something like this. Finally, it is sign function, but inside there is another sign function. And finally, see, this sign function can take value only +1 and -1. When x is positive, I mean non-negative, then it is 1. When it is negative, it is -1. Yeah. Completed state is this. Quantum state and some parameter, other parameter lambda, where lambda takes value from -half to +half, and lambda takes value, rho lambda is uniform. So see, so this suggestion is such that for every possible m dot lambda, finally it will give a value either +1 or -1. It gives a definite value, +1 or -1 for every observer. But challenge is you have to reproduce quantum mechanics. And indeed reproduce quantum mechanics. So finally, you have to integrate over rho lambda d lambda, and finally you calculate this thing, because the sign function in this whole region, integration region, some places it will take plus value, in some places it will take minus value. You have to break the integration, and finally you get in hence quantum statistics. But even apart from this Bell's inequality, I was telling that if I assign definite values, how quantum mechanics will be able to discard it. And it is a definite model where you can assign definite values to all possible sigmas, and at the same time you can reproduce. Yeah, I have taken one case where n dot m is negative, then another case has to be solved for n dot m is positive. This integration will work. Oh. Maybe we can discuss later. Is a scalar product.
Lambda is not restricted. Lambda is complex.
Actually, Bell considered it to be another unit.
Right. But I'm just saying now, let's go and let's assume that this hidden variable. Because I understand physically that's what you're going to think, but you don't know nature.
That's why Bell's theorem is important.
No, I understand that. But my question is, just say mathematics.
But question is that it's for single particle. Yeah, it's for single particle.
Of course. But what I'm saying is, if it is local, but it's a strange object. I don't know if you've thought about that. I'm thinking right now, because I never thought about that.
Yeah, I'll come to the point. Yeah. Now we dealt with only 2 dimensions. Let us go to 3 dimensions. 3-dimension situation is different. And I will tell you that giving definite values to Hermitian operators is equivalent to giving definite values to projector. Because the spectral representation, if you think about it, so if A is equal to A1, then P1 is equal to 1 and rest of the P's are 0 because they are mutually exclusive. So giving definite value to self-adjoint operators is equivalent to giving values 1 or 0 to projectors, because projectors can have two possible values, 1 or 0. So this is equivalent. So you consider a situation, you take three-dimensional system and consider phi 1, phi 2, phi 3, which are orthogonal, and you consider this projector, and this is actually define a measurement, no, P1, summation of P1 plus P2 plus P3 is equal to identity. Now my hidden variable theory has to assign value to P1, P2, and P3, but it can assign 1 to one of the projector and 0 to the rest of the projectors. No, because they are mutually exclusive. Because if an observable has 3 eigenvalues, A1, A2, A3, then our hidden variable theory will assign either A1 or A2 or A3. It is equivalent to tell that it will assign value 1 to one of the projector and 0 to the rest of the projectors. Now, so your theory has to assign definite value to P1, P2, P3, but you can define another resolution of identity where P1 is common, because with this phi 2 and phi 3 you can construct two orthogonal states taking their equal linear combination. Then my hidden variable theory has to assign definite value again to P1, Q2, and Q3, but P1 is common. Question is, two contexts are different also, no? Now, question is, so I can perform measurement in B1 basis as well as I can perform measurement in B2 basis. Question is, which did not arise for 2 dimension. Question is whether my theory will assign values to P1, which will depend on the either it appears in the first measurement or it appears in the second measurement. It changes or it does not change. That means whether my hidden variable theory assigns value P1 independent of in which of the measurement setup it has appeared. Then it is called non-contextual value assignment. Things are clear? Because P1 will appear in both. But question is, so hidden variable theory will give a definite value to P1. If my hidden variable tells, no, when it is in the first measurement, then my hidden variable theory gives is 0. And in the second measurement, it gives 1. Then it will be contextual hidden variable theory. But that seems to be very bizarre kind of thing. Your temperature will be 1 in this context and another in another context, like something like that will be very bizarre. It's not reality which comes to our mind. It is a kind of reality also, contextual reality you can tell, but we don't, our mind don't accept. So reality should be something which is independent of context. So in this non-contextuality implies that to a projector, when you are assigning a definite value, that value has to be independent of the context. Now, Bell showed in a very complicated way, Kochen-Specker in 1967 using 117 projectors. He has a different, they have a different representation, but it can be equivalently told. Like using 117 projectors in 3 dimensions, he could prove that non-contextual value assignment is not possible. That means non-contextual hidden variable theory is not possible. Now we agree?
course, no, I agree on that, but that was not my question.
Yeah, we'll come to that next part.
But my question was related to the constraint of the local variable field to be lambda that are based on principle. Nobody told you that it should be like that. Very simple.
But Bell's theorem deals with lambdas in such a way, lambda can be any mathematical object. Only condition, what you are putting, that is important. Lambda can be any mathematical object.
Right, but
So,
quantum mechanics works because quantum mechanics is defined over the complex, the field of the complex. That's the closed, is algebraic closed.
but again, you are going to features of quantum mechanics. Question is whether quantum one probability rule I can reproduce with an alternative theory which has reality. And we saw that, we will immediately see that it is not possible if you take non-contextual hidden variable theory. Later I will come to the point. Yeah. But fortunately, in 1996, Cabello, I should have put the reference, forgot to. Cabello chose 18 projectors. Projectors means you choose these vectors. Vectors has not been normalized. You can normalize it. So you choose 18 projectors in 4 dimensions, and you can show that non-contextual value assignment is not possible. And projectors are nothing but projectors on these vectors. And rule of assignment is, so I have, for simplicity, I have written V of phi 1, but actually V for this projector. Value assigned to this projector, phi 1, phi 1. And it can be 1 or 0. But some of them has to be 1.
Projectors all commute with each other?
No.
They don't, right?
No. So different set you can construct. With 4 projectors, you can construct different set. So this has to be obeyed. Now you come. So you can check that phi 1, phi 2, phi 3, phi 4, they are orthogonal. So phi 1, phi 2, phi 3, phi 4 are orthogonal. So we assign values to them. This sum is equal to 1. Again, phi 1, phi 5, phi 6, phi 7, they are orthogonal. And again, if you assign value, it will be 1. And you can check that every projector has appeared twice.
Each such set is a context. Right?
Yeah, each such is a context. And each set is orthogonal set. And you go by this, and you can check that every projector value of every projector has appeared twice. Because there are 18 vectors, and here are 36 elements. So every projector has appeared twice. But if you sum them, then left-hand side you are going to get, because value that can be assigned will be either 1 or 0. So left-hand side will be even, right-hand side will be odd. And you are going to get a contradiction. So if added, the left-hand side is even and right-hand side is odd. It shows that non-contextual hidden variable theory in general cannot reproduce quantum mechanics. So you need not go even to reproduce this thing. It can be discarded before that, because it is inconsistent. It keeps inconsistent. Now I am coming to before telling Bell's inequality, I am coming to a very, very elegant. Actually, I worked on Hardy's non-locality. Sometimes it was considered that Hardy's non-locality is the best version of Bell's theorem, at least told by David Marmin. But I find that there is a proof by McConey based on the proof given by David Marmin in 1981 or 82. But this is the most elegant proof that I saw. So this is a system So there is a source, two particles are going, one is going to this side, one is going to this side, and there is a measurement setup. And measurement setup, three possible measurements set up on this side, and three possible measurements set up on this side, 1, 2, 3, 1, 2, 3, and results can be either +1 or -1. Here also result can be +1, -1.
Not that you measure the same thing.
Yeah, it is
When you
prepared.
replica,
Yeah.
perform one measure.
So there is a preparation procedure, and by that preparation procedure, particles are sent and it is repeated. And these also repeated, like choice of setting on each side are completely random, and the statistics will be collected by running the experiment many times. Now, after collecting the measurement statistics, you saw this picture. So you repeated the experiments, these fellow choosing randomly, these fellow choosing randomly, and you are collecting the results, say 1 lakh times. You repeated the experiment and collected the results, and it has two features. When they chose the same setup, the outcomes are same. And second feature is the probability of having the same outcome on both sides for different measurements is 1/4. When both choose one, either both get up or both get down.
Quantum mechanics, one of the central issues is that you perform a same measurement, same different results.
No, if you take the state 5+ that I described, if both measure sigma z, then both can get same results, because the results are correlated. Yeah, for a definite preparation. Yeah. Measurements can be chosen, three possible measurements on both sides. No, it is Bell state. Because measurement, there is not three parties, three possible measurements.
State. Down, down, up. Correct. And if I take the right entity, the right spin, measure sigma x. This particular measurement of sigma x right, plus sigma x minus. Different measurements will give me different results. Statement number 1.
If you take 5+ and if you perform measurement in same direction, or you take single state, if you perform measurement along same direction, results will be always anti-correlated. So it is not going against quantum mechanics. Yeah, but let us pause. Now, Bill.
That statement number 1 is for the statistics.
Yeah.
So it's not for the results of individual measurements, statement number 1. Like it's written about that. It's for the statistics generated from the measurements.
Yeah.
So the statistics will be fixed for some setting.
No.
Saying that if you measure sigma x on both sides,
it can be also sigma.
That's what he means by the same. The outcomes from the two sides
Which is not written correlate.
Yeah, same means if it is up, it is also up. Down, it is also down. That's it. And second statement is something like that. And the Bell theorem tells that these two properties are in contradiction with the following assumption: locality, reality, and free will to choose the setting. It was not explicitly mentioned in Bell's theorem, but this should be there, that I can choose among the three setup, I can choose randomly according to my will. This may be a very strong assumption that someone may tell that God decides what you choose, but you have to choose it. Now you see, what are the possible value-based assignment for Alice's side? For 3 observable, 1, 2, 3. Both can be plus, 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 plus 1, plus 1, plus 1, plus 1, plus 1, minus 1, plus 1, minus 1, plus 1. In this way, how many? 8 possibilities are there. And this side also, 8 possibilities there. So as a whole, how many possibilities are there for if you consider the whole system? 64. No. But I am telling, out of 64, only 8 will be allowed because of this first condition. Because when this is plus, 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 on the other side, it has to be plus, plus, plus. Otherwise, first condition cannot be met. If for the first particle it is plus, plus, minus, then this side it has to be plus, plus, minus. So only these 8s, out of 64, only these 8 will be allowed because of the first condition.
Which is that if you already measure property 1, Alice measures property 1, you also cannot measure property 2 or 3 on the same particle.
No, no, no. It is now I am coming to the more fundamental theory which give value. And now I'll show that.
Oh, this is the deterministic.
Yeah. And also locality assumption, because once you have assigned value, it does not depend on measurement chosen on both sides, and similarly, vice versa. So only these 8 possibilities are there to satisfy the condition 1. Now let us see. Now these 8 possibilities may come with some probabilities. This first one you tell it is first, second, third, fourth. In this way, you can tell P1, P2, P3. Yeah. Now, this assignment or this can appear with some probabilities. So P1, P2, P3, P4 up to P8. Now, if you calculate the probability when Alice choose 1 and Bob choose 2, what is the probability of getting the same results? Then you can go back to, so when Alice choose 1 and Bob choose 2, you remember this thing, and when their results will be same, from where it will come? From P1 it will come, no? With P1 probability, if this is the value assignment and it happens with P1 probability, then in this case, if Alice measures 1 and Bob measures 2, results are same. Similarly, it will come from here, it will come from the last one also, and it will come from other two, 7 and 8.
You assume, you impose the fact that the measurements of Alice and Bob are identical.
No. It's completely random. But they write the results, write the what measurement they have performed and write the results also. Then I collect them in a room, and starting that their results, I got this feature, 2 features. No. I am telling only these 8s are allowed, and they will occur with certain probabilities.
Only the 8 possibilities are allowed. Then by construction, whatever Alice measures, also Bob measures.
This fellow from 1, this. Yeah. In this way, you can calculate this thing and use sum of them. But don't take that this sum has to be 1 or something like less than 1, because this is not for mutually exclusive event. So I am summing them and I am getting this thing, and finally I am getting this thing. And you see that even if P1 and P8 is 0, even this sum of these quantities is equal to 1. Alice choosing 1, Bob choosing 2, and they are getting same result.
They measure the same observable.
No, different
Alice
observable.
measures sigma X and Bob measures sigma Y.
Something like that. But it is, I am not talking about quantum theory, some measurements. So sum of this thing has to be greater than equal to 1. But if you go to the second condition, if you sum of them, it is 1/4 plus 1/4 plus 1/4, 3/4. But according to local hidden variable theory, it has to be greater than equal to 1. McCone in 2013.
What?
McCone, MSCCONE something. MACCOCONE. But it was, in some sense, it was in Marmin's work in 1981 AJP, American Journal of Physics.
Yeah, but Mermin did it.
No, he used the same setup, but this
Yeah, no, but
not these two,
way.
not these two. Maybe first one and second one is something different, but it is very elegant proof. Now question is whether quantum mechanics satisfy these two conditions. Huh? Yeah, no, but you have to show that quantum mechanics indeed can reproduce these two correlations. And of course, pi plus state can reproduce this kind of correlation. Only basis has to be chosen very carefully. So this pi plus can be written in A0 A1 basis, B0 B1 basis, C0 C1 basis, and your setting 1 means measurement in this basis A0 A1, setting 2 means B0 B1, and setting 3 means C0 C1, where A0 is 0, A1 is 1, and some linear combination of them gives you B0, some, and this orthogonal gives you B1, and some different linear combination gives you C0, and this orthogonal gives you, this should be C1 because of copying. And you can calculate easily. So see, if Alice measures setup in setup 1 and Bob measures in setup 2, and same measurement results will be, probability of getting same measurements, same results will be 1/8 coming from here and 1/8 coming from here. So 1/8 plus 1/8 is equal to 1/4. In this way, every cases, you will see that if they choose different setting, probability of getting same results will be 1/4. So quantum mechanics has indeed contradiction with local realistic assumption. Yeah, repeat. No. You have to choose the entangled state, appropriate entangled state, and you have to choose the measurement very appropriate way so that you can get these statistics. It is not that you take into arbitrary sum state and arbitrary observable. Generally, you will fail. You have to choose very carefully. This 5 plus state and observable have to be chosen for setting 1, setting 2, setting 3. That have to be chosen very carefully to get that statistics. And there may be some entangled state, mixed entangled state also, which has no contradiction with local realism. So entanglement and non-locality is not a same concept. I mean, entanglement and violation of this local realism is not. So, entanglement is more general concept. Now, so maybe some 20 minutes I can talk. Another 20 minutes. So another 20 minutes I can talk. Another 20 minutes. Yeah. So to understand Bell game, when I started understanding Bell's theorem, this kind of nice thing was not there. But now you can design a game. Like, let Alice is in one row, Bob is in one row. Alice will be given some question which can be randomly either A1 or A2. Similarly, Bob, B1, B2. And their answer is not something logical. Their answer is either +1 for both the question. Answer can be either +1 or -1. But there is one condition, that after the game starts, you are not allowed to use your mobile. I mean, if Alice gets A1, Bob does not know what Alice has got because their mobile has been taken away. Now, what is the winning condition? Winning condition is, so it will be randomly played. So there are 4 possible pairs. This fellow gets A1, this fellow gets B1. This fellow gets A1, this fellow gets B2. This fellow gets A2, this fellow gets B1. There are 4 possibilities. And it is completely random. That's why 1/4 cases, it will be A1, B1, 1/4 cases, A1, B2, something like this. Yeah. Now, winning.
A1 and B1 are variables that can assume the values of +1 or -1.
But you can, for the timing, you can take simply, give me the value of A1. You have to give me the answer, either +1 or -1. Whatever comes to your mind, I'll collect the answer. But there is a winning condition. Winning condition is something like this. In those cases where Alice gets A1 and Bob gets A1, 1/4 cases will be like this. In those cases, in every cases, product of their answer has to be +1. Individual answer is right or wrong, this is not important. This is not taken care of. Only product will be checked. So first 3 cases, in all cases, product has to be +1. But for A2, B2, again, 1/4 cases, they will get A2 and B2. In all those cases, product has to be -1. Question is whether you can win this game without communication. What is coming to your mind? Can you give me a strategy that by this strategy we can do it? One strategy you can take, whatever question comes, you tell +1. Then in how many cases you will be successful? 3/4, 75%. Because first 3 conditions will be met, but last one will not be met. So you have to, so do you think that if you are given time, then you can devise some strategy so that it can be fulfilled? But it is not. Because at a certain turn, say Alice has decided to give an answer for A1, you give it B of Alice, and this is the answer for A2 by Alice, and similarly for Bob. Now, question is, Alice's answer cannot be function of B1 or B2. This is the problem. Alice's answer has to be locally determined. Now you see, so Alice has decided, okay, this turn I will give this value for A1 and this value for A2. Which question will come, I don't know. So I decide this thing. Bob also decides locally. But all the four, any pair may come out of these 4 possibilities. So if they have to win this game, then their answer has to satisfy all these 4 equations. But you see, if you take the product of this equation, every answer has appeared twice. So left-hand side will be +1, right-hand side will be -1. So there will be no strategy that you can. And not only that, actually 75% is the highest. This is the highest probability if you use classical world correlation or local realistic correlation. And say, so now we consider a local deterministic correlation. So A1, A2 has a definite value. Similarly, B1, B2 has a definite value. Again, there are 4 possibilities here. There are 4 possibilities. So there are how many more, for the joint system, there are how many possibilities? Earlier it was 64, now it is 16. So plus, 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 minus, plus, plus, minus, plus, like that. There will be 16.
Even with the hidden variable theory, you cannot do better than 75%.
That is the Bell's theorem or Bell's inequality. Yeah. So if you name them as 1, 2, 3, 4 up to 16. So if you take a particular correlation and if you calculate this quantity for a kth correlation, whichever you take, this value, this is just a number. If you calculate this quantity, it will be either +2 or -2. If you calculate these quantities for any kth correlation. So consider the first one, +1, +1, +1, +1. You put it here, you will get +1, +1, +1, -1, so it will be +2. Because this is very simple. You take pKa1 out, then it will be pKb1 plus pKb2 and here pKa2 out. So pKb1 minus pKb2. Whatever value you assign for this, one of them will be 0. So it will be finally +2 or -2. And if you calculate this average, so let the kth correlation is coming with probability pk. So if you calculate this quantity, this quantity should be calculated in this way. So now you calculate this Bell quantity. A1, average of A1, B1, A1, B2, A2, B1 minus A2, B2. And your pk is independent of AI, Pj. Because as I told, free will is there. And finally, actually averaging over +2 or -2. So the average is bounded by -2 and +2. And it is famous Bell's inequality, but you can express this thing in terms of the game also. Like this is Bell's inequality, but this average of AI Bj can be written as this thing. Because when the value is equal, then product is +1. When value is unequal, product is -1. So P of value of AI is equal to value of Bj minus probability of value of AI is not equal to value of Bj. In this way, and this is normalization condition because there are only two possibilities. And from there, actually, you can express your average in terms of probabilities like this. And finally, you get this thing. So this is so 1/4. So all the cases will appear with probability 1/4. And this is the success of your winning the game. And it is bounded by 3/4. So 75% by any locality.
Just to make sure, a winning probability don't mean to get 4, you mean to get above 2.
No.
What is it?
Yeah, no, I want 4. Or winning probability 4.
4.
Yeah.
So
yeah. When this is satisfied, this quantity becomes 4.
And you are allowing for a game where the choice of helix of E1, for example, is probabilistic. Namely, each step when you collect statistics,
it can be probabilistic, but again, it is local. So I have written that proof, but finally I thought that I will not get time. That's why stochastics part I'm not going to say about stochastics, but that is also true. Sorry. So John as well derived this inequality in 1964. Not exactly this inequality. Actually, this inequality was derived by CHSH in 1969. So Bell's inequality implies that for any correlation for which this quantity, again I have made a mistake, is strictly greater than 2, cannot be expressed as mixture of deterministic local correlation. So to explain this thing, let me take another nice correlation by which you can win this game perfectly. So consider a correlation like this. If it is, so it is here two sides. Here input can be A1, A2. Here input can be B1, B2. So there are four possibilities. But for these first three possibilities, it is correlated, either plus, plus, or minus, minus, but happens with equal probability. And for A2, B2, it is anti-correlated, but again, two things happens with equal probability. Then if you have this kind of correlation, you can win this game with 100%. Because for first case, product will be +1, second case, product will be +1, third case, product will be +1. But for the last case, product will be -1. That is the exactly winning condition of the game. But this is a very nice correlation. It has no contradiction with relativity also. Everything is completely random. By making by giving some input, looking at the result, you cannot tell which input has been given on the other part. So it is very nice correlation discovered by Popescu and Rawlik in 1996 or 1997. But nature does not allow this correlation to exist. If it allows...
Sorry, I don't understand. If you look at the first line, you have two possibilities, plus, plus, and minus, minus.
And
so
correlated, but with equal probability. It is...
But then they need to know.
No, I am telling say it is a magic box. There is some input, there is some output, and magic box is giving a correlation like this. Then I am telling if you have this magic box, you can win this game with 100% probability.
That is cheating.
Yeah, it doesn't exist. But this correlation is consistent with relativity principle that I am trying to emphasize.
You have, let's look at the first line. So let's say that Alice had +1.
First line tells that if Alice gives input A1, Bob gives input B1, then their results will be both +1, +1, or both -1, -1, but with equal probability.
But they need to have some correlation, because if Bob measures...
No, I am telling, so that's why I am telling, you consider only this correlation. I am telling that this correlation does not exist, but
So there is correlation. So there is some correlation.
Of course, but this kind of correlation does not exist in nature. I am just
Imposing this correlation.
Yeah.
That's the optimal way.
Now, if you want to break this correlation if you want to express this correlation in terms of deterministic correlation, then the only possibility is these two. If you take equal mixture of this correlation, you get this correlation. But this correlation has a peculiar feature. It violates relativity. Both of them violates relativity. See how? You take one case. See, a part of that first correlation. If this fellow measures A1, this fellow measures B2, it is +1, +1. If this fellow measures A2, but this fellow measures again B2, it is +1, it is -1. So they can design, they are far away. If this correlation could exist, then they can send some information. Alice can send some information. Alice will tell India, when India has won the match, Alice will measure A1. When India lose, Alice will measure A2. But Bob will always measure B2. If Bob gets +1, he will know, yeah, India has won. If he gets -1, he will know that India has lost. This kind of correlation, if it exists, then you can instantaneously transfer information from one place to another place. So this is non-locality. So interestingly, this violates Bell's inequality maximally. That means it reaches to the algebraic maximum 4. But if you want to break this correlation in terms of deterministic correlation, that deterministic correlation becomes non-local. And if you use quantum strategy, I'm not going to tell in details this quantum strategy. You have to choose some spin observable on Alice's side carefully and some observable spin observable on Bob's side carefully. And if you play the game that was posed earlier, that if question 1 comes, then I will perform this measurement. If question 2 comes, I will perform this measurement. And my answer will be, if it is up, then I will tell +1. If it is down, I will tell -1. In this way you can do, then by using quantum mechanics, you can win this game by 85% probability. So you can increase 10% from. That means it is equivalent to that Bell's inequality achieved can be value of this Bell's inequality in quantum mechanics can achieve 2√2. So now Bell's theorem is telling if one wishes to realize certain quantum correlation as mixture of deterministic correlation, then some of the deterministic correlation will be necessarily non-local. See, this is very, very powerful correlation, non-local correlation. If you want to realize them in terms of deterministic correlation, both of them become non-local. But quantum mechanical correlation is not that powerful. But if one wishes to realize certain quantum correlation as mixture of deterministic correlation, then maybe not all the correlation becomes non-local, but at least one of them has to be non-local. That is, when the Bell's inequality is violated, then if you want to write that correlation in terms of deterministic correlation, then at least one of the deterministic correlation has to be non-local. So conclusion, though quantum mechanics does not allow signaling, so entanglement, whatever powerful it is, it does not allow signaling. It does not violate relativity principle. And that's why Einstein was trying to prove that quantum mechanics must be non-local. In an explicit way, he could never show. But I am surprised to see that even that time other physicists could not pose this question, could not ask this question to Einstein, show that quantum mechanics has certain non-local feature. So what are the allowed theories? Allowed theories, local but not real. So quantum mechanics does not allow signaling a standard quantum theory, but it is not real. Value as every observable does not have a definite value. So it is not real. It is a standard quantum mechanics. But there is another quantum mechanics, real but non-local. This is Bohmian quantum mechanics. Bohmian quantum mechanics uses this hidden variable as position, psi, x. This is the state. But it is real but non-local. And you can have a theory which is both non-local and non-real, but that will be not. But it is allowed. Yeah. Now, my last point is, does the impossibility of joint measurement of some observable have any role to play in Bell's theorem? And it has been proved in I forgot the year, maybe 2000 or 2001. Now you are forgetting about hidden variable theory. You are taking a theory. If that theory allows joint measurement of any two observables, and theory also respects no signaling condition, then it implies that there is no violation of Bell's inequality. Any theory which allowed joint measurement and respect no signaling satisfy Bell's inequality. And you know that quantum mechanics violates Bell's inequality. Then what conclusion can you draw? So if quantum mechanics violates Bell's inequality, then one of them has to be discarded. Which one you are going to discard?
Can you explain what you mean by joint measurement? Because always say point separation. Suppose I want to measure sigma.
Joint measurement with I want to construct a joint observable which will measure sigma x and sigma y at the same time. So 4 outcome observable.
So, you know that in physics, regardless of commutativity or not, when we are talking about same point or same time, we continue, we always like to
no, here the meaning is whether you can construct a joint observable, which will imply measurement of sigma x and sigma y both. Now I am trying to tell that if some theory allows joint measurement and it respects no signaling, that it implies.
What do you mean by joint?
Joint measurement.
What do you mean by joint measure?
precisely what do you mean by joint measure?
I think that he means that there is an instrument that can measure, it's not just a Stern Gerlach here and a Stern Gerlach here. There is a measurement that is measuring, it's an instrument that is measuring these two things together. That's what he means by joint measure.
So for spin, it will be 4 outcome measurement.
Yeah, but I mean, that doesn't exist, right? That's
Yeah. So if now we know that quantum mechanics violates Bell's inequality, then what is your conclusion? Because already quantum mechanics is no signaling theory, it respects no signaling theory. So you will come to the conclusion that certain joint measurement is not possible in quantum mechanics. But this very, very powerful violation of Bell's inequality by statistics collected from real experiment establishes that there are indeed some observable whose joint measurement is prohibited by nature. So sigma x and sigma z is a mathematical representation of spin measurement along x and z. Maybe quantum mechanics in future may be replaced by some other theory, but measurement along spin measurement along x and spin measurement along y or z, that will remain. And when statistics violate Bell's inequality collected from quantum mechanics or collected from nature, now you are, because they got this Nobel Prize because they collected the statistics from nature. And now you can tell that quantum mechanics may be replaced by some other theory, but that theory even will not allow joint measurement of certain observables. So when quantum mechanics was being discovered, then intuitively Heisenberg was thinking that there will be certain observable whose joint measurement cannot be performed. But he has no mathematical formalism at that time, but at least intuitively. But now you can tell them, of course, non-commutativity you can use now, but that is a mathematical artifact. Quantum mechanics may be replaced by some other theory, but still there will be some measurements in nature whose joint measurement will not be possible. That is established and that is important. Yeah, I have finished.
So I'm still trying to understand this joint measurement. I mean, measurement for me is part of the measurement is a unitary operator of the form exponential of I times dt. dt is the time of the measurement, times operator of the system, times operator of the detector. So let's call it O times A.
Not operator.
It can be a spin operator. So now you are telling me that I have two measurements. So I have O1 operator on the system times A, and I have O2 times B. A and B are the qubit, the detector operator. So now I have two options. Either to say that I have exponential of I O1A times exponential of I O2B, or that is exponential times exponential, or to put the two in the same exponential. So I can have exponential of I O1A plus O2B. No, if I took the second one, it's not. It's not. I mean, it's not,
because otherwise you're measuring only one. That is
precisely. This was my point. So if I have two measurements, now I need to decide whether I put O1 e to the I O1A times e to the I O2B in this order or the opposite order. So by construction, I mean, mathematics tells me that I need to decide which one I put first and which one I put the second. So I don't. So by this.
But this has the power. But this can be derived without using any mathematical formalism. This very general kind of statement, independent of any particular theory.
That's a point.
Use the microphone, please.
A naive question, but this Bell's inequality also, I mean, there's an underlying assumption about the dimension of the Hilbert space, right? So it's either +1 or -1. So what I have proved is that in two-dimensional systems or qubit systems, this cannot happen. But is there a Bell's inequality for higher dimensional systems?
That will be more complicated.
But so this only this proves that for two-dimensional systems, quantum mechanics behaves a certain way. But for higher systems is okay. So there is something.
That will be more complicated. Yeah. Yeah. No, Bell's inequality was more particular. CHSH is the most general. Bell's inequality was very particular thing, what Bell discovered in 1964. But Bell himself derived also this CHSH later.
It's a series of inequalities by Fermi.
Yeah, that involves n particle.
So there are generic